Okay. Good afternoon, class. Okay, so as you can see, we are looking at spanning sets of vectors. We are looking at spanning sets of vectors. I think during the previous meeting, the definition for spanning sets was given. And we said that if you are able to express some set of vectors as a linear combination of another vector, then we say that those set of vectors spans with the vector that is given. If you're able to express such vectors as a linear combination, and when we talk about linear combination, we are looking at scalar multiplication of some set of vectors. So that is that. When that condition is satisfied, then we say that those set of vectors spans with a given vector. Okay. So we will go through some series of examples. And then after, if there's any question, you can raise your hands or you can also type, and then we will look at how those concerns can be addressed. All right, so we will take our first example. So these are the set of vectors that are given, and we are to show that this set of vectors spans with the vector that is given. So we express this as a linear combination of this vector. So it's going to be 24, and this is what? A two-dimensional vector. And then we express these other vectors as a linear combination. So it's going to be 1, 3, and then you give a scalar, any scalar, so we can use say x to represent the scalar, then plus the other vector. So y. So we have y, then 2, 5. So from here, we are now going to form our augmented matrix, a 2 by 2 augmented matrix to find the unknowns. And if you're able to find the unknowns, you will now replace them here and then add them. If you're able to get this vector here, which is 24, then it has really confirmed that this set of vectors has formed or expands with the vector 24. So let's move ahead and then we solve. So this is a scalar. So it's going to run through the vector that is given. So we are going to get x 3. So we are going to get 24 equals x, this multiplying 1, so x, and then x is also multiplying 3, so 3x plus the scalar y also run through the vector given, so 2y and then 5y. From here, we can now add the set of vectors. Can now add the sets of vectors. So from here, it's going to be 24 equals x plus 2y, 3x plus 5y. So we can find the augmented matrix so that we solve for the unknowns, which is x and y. So let's form the augmented matrix. So we have 1, 2, and then 3, 5. Multiplying the vector x, y should be equal to 24. Write it before or after, it's still the same thing. So from here, we will now interchange the vector xy to replace 24, will now replace the vector xy, and then it will form the augmented matrix. So 3, 5 augmented with 24. So I think we've gone through this series of processes before. So it's not a new thing. The same thing as we finding the RREF, the same process we are going through. So it's not a new thing. So from here, we are now going to find the RREF of this vector, of this matrix, which is a 2 by 2 matrix. So if you're able to find the RREF of this matrix, you realize that this side will also change. This two-dimensional vector will also change, and that will be the value for x and y. Okay, so let's make progress. So we want to change this to 0. So how do we go about it? We can multiply root 1 by the negation of the 3. So we can say that root 2 implies negative 3 of root 1 plus root 2. And then we get this side to be 0. So we are going to get 1. Root 1 was not changing. So it will still be the same thing. Now let's focus on root 2. We are now focusing on root 2. We are saying that root 2 is negative 3 of root 1. So that's going to be negative 3 plus root 2, which is 3. So it's going to be 0. Then the second one, we are also going to get minus 3 of root 1. So that's minus 6. And minus 6 plus 5. We are going to get negative 1. We are going to get negative 1. Then we make progress. We are also looking at negative 3 of root 1, which is 20. So minus 60. So we are going to get minus 60. Then plus root 2, which is 4. So we are going to get negative 56. Negative 56. We are going to get negative 56. So we can see that we can also get our leading one here by multiplying root 2 by negative of what? Root 2. So that we get the leading one for the second column. So from here, we can say that root 2 again implies negation of row 2. So that this side will now change to be positive. Now change to be positive. The idea is that we are going through this process to be able to get our unknowns, or the unknown scalars. Okay. So from here, we are going to get the 1 is not changing, still the same thing. We have the 20. Then we are just running negative, we are negating row 2. So still 0, positive 1, and then you get 56. So from here, you can decide to proceed to get the RREF, or you can apply the Gauss elimination. So with that one, all that you need is the REF, which we have gotten. We have gotten the REF. So all that we do is that, remember, this column represents your X column, and then this column also represents Y. So you can say from here that Y is equal to 56. So from here, so from here, we are proceeding up here. We are going to proceed here. So we are going to get Y equals 56. So our Y is 56. It will not capture the whole body. It's okay.
Screen is not visible.
It's not visible. It's okay. Okay, so let's make progress. Okay, so from here, we've gotten our Y to be 56. We proceed to get X. So we can go back and write this expression for the row 1 again. So the row 1, the expression for row 1 is X plus 2Y X plus 2Y, which is equal to 20. We are writing the expression for row 1 again. But remember, we've gotten the value for Y. So we can just substitute here and get X. So you are going to substitute the value of Y, which is 56. So X plus 2 multiplying 56 is going to be what? 20. So it's the understanding that is very important. We have gone through this series or this similar approach almost all our topics we are looking at. So it is not a new thing. Just follow the same steps. It's the understanding that is really important. So from here, we are going to get X plus, then multiply 56 by 2. We are going to get 112. So we are going to get S plus 112 is equal to 20. Then from here, we can make X the subject. So X is going to be 20 minus 112. So X is going to be minus 92. We are going to get X to be minus 92, and then our Y is also known to be what? 56. So all that you have to do is to come back here and substitute the unknowns we have gotten, the values for X and Y, and then you add them. If you're able to get the 24, then we can now conclude that the set of vectors that was given in the question spans with this vector that is given. So we are going to test and to confirm. So we now know the value for X, we know the value for Y. So we just have to substitute. So 24 equal to minus 92. plus 2y, which is 56. And then we are going to get 3 of x minus 92 plus 5 of y, 56. So from here, you now simplify. If you simplify, so if you simplify this, you can take the calculator. So if you simplify here, if you get 20, then it means that we are, so we've gotten the 20, so let's progress. So if you add all these, you are going to get 20. And then you also add this one and see if you get 4. So you get 4. So once this set of vectors with the scalars that was unknown, but now we've been able to identify these unknown scalars. And by replacing them, we have gotten the vector that was given in the question. So what it means is that you can now conclude that the set of vectors that was given spans with the vector 24. So you conclude that the vector 1, 3 so therefore the vector 1, 3 and then we have 2, 5. So this set of vectors 1, 3 and then 2, 5 spans the vector 24. So this is how the conclusion will be. So that is that. That is how the conclusion is going to be. So I think I'm good. So if you have any question with regards to this example, you can now ask. You can raise your hands. Oh, okay. So if you have any question, you can raise your hands and then you will now be unmuted and then you can ask your question. So if you have any question, you can raise your hand and then we'll look at that. With regards to the example we have done, if you have any question, you can now look at that. Some people can check. Yes, Albert.
I should take who was first. Send this
Okay.
one.
Oh, I think you asked him to unmute, so you unmute himself. Okay, so FMS 017419. Who has to respond? Reactions. Yes. Who is speaking?
Hello. Can I talk?
Yes. What's the question?
To be 0 and 1. Can you
Please speak loud. I can't hear you well.
so the 2 to 0? It is
Tell him to type it.
no, sir.
Yes, I'm listening.
I'm saying that after making the second row,
Okay.
the first row, the 2 can you 0?
Is you looking at the second row?
Yes, the first one, can you change the 2 to 0?
Can you change the first one 2 to 0?
Yes.
Which side?
Is it the row echelon side? How is what?
Which two dice you say change to 0? I didn't do it.
Tell him to.
Is it going through the row echelon operations?
Yes. Yes.
And then, yes, you are saying that which parts?
I said the first row.
Okay.
I mean, the first row is 1 and 2. So can you change the 2 to 0?
Oh, okay. So you are saying that the first row is 1 3.
1 2 1 2.
1 2.
And the second one is 0 1.
1 2, and the second one is 3 5.
Yeah. So
And you are saying that can you interchange them? Is that not it?
No, I'm asking that.
Yes, carry on.
I'm asking that after changing your second one to 0 to 1,
Okay.
can you change the first one, the 2 to 0?
So are you talking about changing it to RREF?
Yes.
Yes, you can go ahead and do that. So you see that where we just use the REF. So you can also go ahead and then change it to RREF, and then automatically the values for X and Y will just be there. I hope you are getting it. And that's the Gauss-Jordan elimination.
Okay. Sir.
So that one, you just get the values for X and Y straightforward.
Okay.
So this one
Okay.
is the Gauss elimination. We are just trying to reduce the equations and also to rewrite again. And by so doing, you will get values for one, and then we substitute and get the other one. Are you okay now?
Okay.
All right.
Thank you, sir.
Okay. So that is that. I think we have to make progress. So let's make progress. You can meet all of them. Okay. So let's get to the next question. After we are done with the spanning of sets, we will now give opportunities for questions. So let's carry on. So let's try this example.
Someone says that we know so why asking?
So please, these processes, I know you will know already. So when I finish with the spanning, the examples we are going through, you can now ask your question. So you hold on with the questions for now. And let's make progress, okay? Okay. So let's look at the second example. We are to show whether or not R2 is spanned by the vector
Answer.
All right, so with this one, we have to show whether this set of vectors 1, 3, and then 2, 5 spans in R2. In R2. So this time around, the vector is not given. As of the initial example we solved, you realize that the 24, that vector was given. So we were to just look at that if we can express the two vectors that was given. If we're able to express it as a linear combination and the result gives us the 24, then you can say that this set of vectors spans with this. But in this case, the vector is not given. The vector is not given. So we are saying that that vector should be in R2. It should be a two-dimensional vector. So in that case, you represent that vector by any variable. So in this case, we are going to use X and Y. We are going to use X and Y. So let this be a member of R2. So we are going to let X and Y represent that vector. That this set of vectors must span with. So in this case, it's a general vector. So we are just representing it by XY. XY. Okay, so we now express this as a linear combination to our XY. Okay, so we write this as it is given. So we are now using XY to represent the vector that this set of vectors must span with. So we are now using XY equal to, then we express these two as a linear combination. So we can represent A to be the scalars, or we can use any other variable of our choice. Then the vector given is 1, 3, which is also a two-dimensional vector. Then plus other scalar. We're also picking another scalar, B. So we are using B to represent the other scalar. And then the vector that is given 2, 5. So now we can now form a system of what? Equations to solve the unknowns. So we are looking at finding the values for A and B. The focus is not finding X and Y. We are finding A and then what? And B. We are looking at the values for A and B. So how do we get A and B? Okay, so let's make progress. So after you have expressed this as a linear combination to the vector which is in R2, you now express this as a linear combination. So we see that this can form an equation, and in this case, it will form what? Two systems of equation with two unknowns. So we are going to get XY should be equal to A, that's 1 times A, then 3A. Plus we have 2B and then 5B. So now from here, you can see that by equality of vectors, we can express the ones at the top to represent one system of equation. So you say that x should be equal to a plus 2b, and this can form equation 1. We can also express the last one also as another equation, another system of equation involving two unknowns. So equal to 3a plus 5b. We are not using the matrix approach in a sense that we don't know the values for x and y, So we are just using a simultaneous approach to solve. So either you can apply the elimination method or substitution method to get the two unknowns. Okay, so let's make progress. So from here, we can make one of the unknowns the subject. So if we are looking at equation 1, so from equation 1, we can say that a is equal to x minus 2b. From equation 1, you can make a the subject. So we are going to get a equals x minus 2b. I can call this equation 3. We have now gotten a third equation. Now, let's also make b the subject from the other unknown. So from here, you can say that once you have gotten this, you can put it into equation 2 rather. So you can say substitute or put equation 3 into equation 2. So we are substituting equation 3 that we have gotten into the second equation. Okay. So from the second equation, wherever we are seeing a, we are going to substitute it by x minus 2b. So y equals 3 multiplying x minus 2b plus 5b. So this is now our new equation for the 2. So let's expand and see. So we get y equals 3x minus 6b plus 5b. We're going to get y equals 3x minus 6b plus 5b. And finally, our y will be equal to 3x minus 1b or minus b. So finally, we are getting y equals 3x minus b. Y equals 3x minus b. So looking at our equation 3 and then equation 4, this is now our equation 4. But we are to express the values of a and then b in terms of x and y. In terms of x and y. So now, how do we express a in terms of x and y? We can do that by substituting the value of b into equation 3. So it means that we must be able to make b the subject in this equation. So from this expression, we say that so b is going to be 3x minus y. So from this expression, equation 4, so let's make b the subject, and then we make that one equation 4 so that it will be easy for us. So instead of us to make here the subject, we are making b the subject instead of y. and then we are going to call that equation 4. So you can see that B has been expressed, or the unknown we are looking for. So one of them is B. We have been able to express it in terms of what? X and Y. And so we leave it as it is, because there's no value for X and Y in the vector that we are giving. So you leave it as it is. Then you go also and make A the subject. We've already made A the subject from equation 3. But you can see that it involves B. But our expression should involve only X and Y. So we are also going to substitute the value of B into equation 3, so that A2 will involve only X and Y. So from equation 3, we will now substitute the value of B. So equation 3 is A equals X minus 2B. But we know the B to be 3X minus Y. We substitute it there. We know the value for B. That is equation 4. We just substitute it into equation 3. So A is going to be X minus 6X, then plus 2Y. We are getting A to be minus 6X plus X plus 2Y. We simplify. So A will finally be minus 5X plus 2Y. So A is finally equals minus 5X plus 2Y. So we have gotten our unknowns. All that we are interested in is getting our unknowns, which is A and B. And we have already gotten that. So we go back to the expression that we stated earlier. We go back to the expression we stated earlier, that X, Y should be equal to A of what? Or we can even use this one. We can use this one. So XY should be equal to A 3A plus 2B 5B. So we are going back to this expression. And then remember that we have gotten our unknowns. So all that we have to do is that we will now assume any vector, that's a two-dimensional vector for our X and Y. You can pick any example you want and just use. You can pick any value for X and Y as your vector. That is what? The two-dimensional vector. And then test. And then you test. So assuming we are picking X and Y 0, 1. We are using 0, 1. If we are assuming X to be 0, 1. So we can pick any vector to represent X, Y. So I am saying that let's vector X, Y be equal to 0, 1. You can use 1, 1, any vector of your choice. But at the end of the day, it should be a two-dimensional vector, because we are working with what? A dimension in R2. So it must be a two-dimensional vector. You can pick any value to represent your X and Y and test. Now, I am using 0, 1. So you go back to the values for A and then B, and then you substitute the numbers you have chosen to represent X, Y. So let me make this one equation 5, so that we will now use it. Equation 5, and then the B is equation 4. So when I refer you to equation 4, I mean B, the expression for B. So from equation 4, we have B equals, as you can see, this represents our X, that is 0, and then our Y is 1, equality of vectors. If you apply equality of vectors, our X is 0, our Y is 1. We just substitute it into equation 4, which is an expression for B. So now 3, we have 3 multiplying X, and our X is now 0. Minus Y. So minus Y, our Y is 1. So this implies that our B is going to be minus 1. So when I picked 0, 1 to represent XY, I have gotten a value for B, which is what? Negative 1. Then also from equation 5, which is also an expression or an equation for A, then we also substitute the value of X and Y. So we're also getting A because we have negative 5. And then of X, our X is 0. You put it there. Then plus 2Y. And then our Y is 1. Our Y is 1. So from here, we are going to get, let me write it here, implies that A is also equal to 2. So you see that if we chose 0, 1 to represent our XY, and finally we've gotten A to be 2, and then B to be negative what? 1. So all that you do is that you go back to this expression. You now have taken a value for XY. You now put it there, which is 0, 1. And then you have now gotten values for A and B. You also put it in. You put it in and to see if you get the same vector. If you're able to get the same vector, then it is true that the set of vectors that is given spans in R2. Okay, so now let's make progress. So we are going to substitute the value of A and B that we have gotten here into the expression or into the linear combination set of equation we have created. Okay, so we have A, we had A to be 2. I'm going to put it there. And then we have 3A. And then, so it's going to be 3 times 2, which is 6. Plus, we also have 2B and then 5B. So 2 times B. B is negative 1. So it's going to be negative 2. And then 5B. We know B to be negative 1. So we are going to get 5 times negative 1, which is negative 5. So from here, you can see that when you add them, and in addition of vectors, it is done correspondingly. So we are going to add the ones at the top and also add the ones at or below, those ones that are below. So let's add them and see. You see that if you add 2 plus negative 2, that is going to be 0. So we have gotten the 0 that is here. The 0 that we chose, that vector 0, 1 that we chose to be our values for X and Y. We have gotten the one at the top. Let's check the ones below. We have 6 plus negative 1. You are going to get 1. So it is true that when we chose XY to be 0, 1, the set of vectors that was given has spanned with what? With the vector XY, which is in R2. So it is clear that if you pick any, vector in R2, then it will span with the set of vectors that is given. It will span with the set of vectors that is given. So you can now conclude that the set of vectors 1, 3, and 2, 5 spans in R2. Spans in R2. So that is that. That is that. Let's make progress. All right. So yes, who is 202001? You have something to say?
Yes, sir.
Yes. What is your question?
Yeah, please. So, regards to the assumption that we made, assuming
Okay.
that x equal to 0 and y is equal to 1.
Okay.
So, in the case of exams, do we have to assume numbers like that?
Yes, you can assume any R2, I mean a vector which is in R2, and you will still get it.
Okay.
Yes, so you can pick
So,
any. Yes.
so in this case, so suppose we assume x to be 2 and y to be 3. So, how will it go?
You also go through the same process.
Okay.
Now you've gotten the value for your xy. You now
Okay.
fix it into the expression of a and b and get the values for a and b, and then you now substitute them and compare if the two vectors are the same. Then
Okay.
the set of vectors spans with the vector that you have chosen, which is in R2. So the focus here is that any vector that you pick as an assumed vector must be in R2, or it must be a two-dimensional vector. Are you getting it?
Okay, sir.
Okay,
Thank you, sir.
so that is that. Okay, so let's make progress. Okay, so let's make progress. Okay, so we are looking at linear independent and linearly independent set of vectors. So we are looking at if you have some set of vectors, under what condition would they be dependent or independent? Now, so let's look at the independent first. Now, a set of vectors, say V1, V2, and many others, are said to be linearly independent if the equation or if the set of vectors can be expressed as a linear combination which is equal to 0. So if we have if set of vectors, so if the set of vectors V1, V2, Vn. So the set of vectors V1 up to Vn is said to be linearly independent. If we can express it as A1 V1 plus A2 V2 up to AN Vn, which is equal to 0. So all that we are saying is that if you have the set of vectors V1, V2 up to Vn, and then you are able to express it as a linear combination. So the A1, A2 up to AN, they are a set of what? Scalars. They are a set of scalars. That is multiplying the vectors. If you're able to express this and it is equal to 0, then you can conclude that the set of vectors that are given are linearly independent. And the 0 vector, which is over here, is or should be gotten from the unknowns. That is the A1, A2. If the unknowns are 0, it is when that will give the result to be 0. So if they are not 0, there's no way this expression can result to 0. So the condition here is that the set of unknowns, scalars, which is A1, A2 up to AN, must result to 0 or must be 0 for the whole expression to be equal to what? 0. So we go through the same process. You take the given vectors that are given, you augment them, and then you find the unknowns, as we did in the case of finding the linear combination, expressing them in the form of a linear combination. If you are able to do that, who is sharing that screen? So if you're able to do that, then you conclude that, and when the unknowns give you 0, then you can conclude that the set of vectors are linearly what? Independent. So let's take some examples and then we look at that. So if we have V1 equals 1, 2, 0. And then we have V2 equals 2, 1, 3. And then V3 equals 5, 3, 4. So we have to determine if the set of vectors that we can see are linearly independent or not. So all that you have to do is to express this set of vectors as a linear combination. Express this set of vectors as a linear combination. So it means that you will generate some unknown scalars to multiply this set of vectors. So we can say let A and B and then C represent the unknown scalars. So we can write it as A multiplying 1, 2, 0 plus B 2, 1, 3. And then plus C multiplying 5, 3, 4. So this is how a linear combination is expressed. So we see that we have expressed these vectors as a linear combination. Then we move ahead and to augment the matrix. So we are going to augment this matrix. So this is the augmented matrix. So the augmented matrix is going to be 1, 2, 0, 2, 1, 3, and then we have 5, 3, 4. Multiplying the unknown scalars A, B, C. So from here, we now interchange or join this one too. So it's going to be 1, 2, 0, 2, 1, 3, 5, 3, 4. Then A, B, C. Then A, B, C. So with this, we go through the process to either to the REF, the row echelon form, or the reduced row echelon form to get the unknowns A, B, and C. So at the end of the day, if here tends to the identity matrix, whatever will be here will now represent. So we are going to write the so if you're able to change this place to the identity matrix, then whatever will be at the other side. So we are saying that it should be equal to what? 0. So it means that this should be equal to 0, 0, 0. So in that case, the augmented matrix here will now be 0, 0, and then 0. So that is how it's going to be. By saying that if you express it as a linear combination, it should be equal to the 0 vector. It should be equal to the 0 vector. So you will now augment the matrix, and this is how it's going to look. And if you're able to get this side to form the identity matrix, and then the values change, we are looking at trying to find the unknowns A, B, and then C. So at the end of getting the values for A and B, and then C, if these unknowns are zeros throughout, it means that if you multiply them by the vectors, we are going to get the 0 vector. So in that case, you conclude that it is linearly independent. So you are looking at the processes that we are going through is to lead us to get the unknowns, which is A, B, and then C. So if A, B, and C are zeros, it means that the whole expression, which has been in a form of linear combination, will also be 0. So in that case, you conclude that it is linearly independent. So if you get any or at least one of the unknowns not to be 0, then you conclude that it is not a linear or independent set of vectors, or it is linearly dependent. So if the expression is not linearly independent, then it is linearly dependent. So that is how we go by these processes. You are going to find the unknowns, which is A, B, and C. If the unknowns A, B, and C are zeros throughout, it means that the expression will eventually also be equal to 0, which is here. If any of the unknowns, if C is not zero and A and B are zeros, the expression is not linearly independent. So that is how it is. That is how it is. So you look at it very carefully. So that is that. And then let's also look at when they are not vectors. When the question involving is functions or they are functions, it means that the dynamics will change. We will look at the processes, how we go through when it is a function. So when it is a function, you can also apply the Roskian method to identify whether it is linearly independent or dependent. If it is a function, you can apply the Roskian method to identify whether the system of functions is linearly dependent or independent. And then another method too is that if we are able to express one of the functions to be a scalar multiple of the other, then you can also help you to conclude whether it's linearly dependent or not. So when it is a set of vectors, as we have done over here, all that you have to do is to find the unknowns. And when you are looking at the unknowns, you go through the REF method or the REF, which is the same as the Gauss elimination or Gauss-Jordan elimination method. You augment it, you transform the vectors to a matrix and augment the matrix, and then you now look at how the unknowns will be gotten. When you get the unknowns to be zeros throughout, then you can now say that they are linearly independent. If the unknowns, if any of the unknowns is not zero, you conclude that it is linearly dependent. It is linearly dependent. So that is that. Okay, so there can be instances where, as I said, the given question will be in a form of a function. If it is a function, for instance, if we are to verify that the given functions we have f, the first function to be expo 2x. We also have the other function f2 to be expo 2 multiplying x minus 1. Now, As I said, if it is a function, as in this case, we have to verify if this set of functions are linearly dependent or not. Now, if we have this, the methods we can apply, there are two. You can either use the Roskian methods, and that one we are looking at finding the determinants of the function, finding the determinants of the function that is given. So we are using the Roskian methods to identify either the set of functions given are linearly what? Dependent or not. So for the Roskian, all that we are looking at is to find the determinants of the functions. So we have function 1 and then 2. Then these are their derivatives. F prime of 1, F prime of function 2. So that is how we go by the Roskian methods. Here is the first function. You put it here. You also have the second function to be here. Then the second row, we are looking at the derivative of the first function, the derivative of the second function, and then you find the determinant of a 2 by 2 matrix. So if the functions are 2, after you have expressed it, you find the determinants of the functions. If you get the results to be 0, then you conclude that it is linearly dependent. It is linearly dependent. If not, then the sets of functions are linearly independent. So let's look at the example that is given. So we are going to look at the function given here is expo. The function given is the f1 is expo 2 to the power x, 2x. So you write it there. Then the second function is also here. You also place it here. So expo 2x minus 1. Then the next row is to differentiate these functions respectively. So we are going to differentiate this function. So if we differentiate this function, we get 2 expo 2x. And then you also differentiate this function. So if you differentiate this function, you are going to get 2 expo 2x minus 2. Remember, if you expand this, you are going to get 2x minus 2. It's the same thing as whatever is here. So we differentiate the exponent, that will be 2, and then you repeat whatever is here. That is whatever is here. Then you now find the determinant. If you get it to be 0, then we say that the set of functions are linearly dependent. Okay, so let's see. Now we have differentiated the function. So let's find the determinant. So cross multiply and then subtract it from the also multiplication of the other two. So we are going to get expo 2x multiplying 2 expo 2x minus 2. Then minus, we are finding the determinant of a 2 by 2 matrix. So minus, then we also have 2 expo 2x multiplying expo 2x minus 2. So it should be equal to 0. So we work towards that. If that condition is satisfied, then we conclude that it's linearly dependent. If whatever we get here is not equal to 0, then we conclude that it is linearly independent. So let's expand and see. Now, if we expand this, we are going to get 2 expo 2x. Since the bases are equal, we can add their powers. So plus 2x minus 2. Minus, we also go to this side. We have 2, the bases are equal. So add the powers. So 2x plus 2x minus 2 should be equal to 0. Now let's simplify and see if we get 0. So you can see that we get 2 expo 4x minus 2 minus 2 expo 2x minus 2 equals 0. So you can simplify here. So expo 4x minus 2 minus expo not x minus 2 equals 0. So from here, you can see that this minus this will give us what? 0. So 0 is equal to 0. So therefore, the condition has been satisfied. And once the Roskian has given us 0, we conclude that the set of functions that is given, that is f1 and f2, are linearly dependent. So therefore, f1, f2 are linearly dependent. So the condition has been met. The Roskian has given us 0. So go through the derivative or finding the derivative, and then finally you are looking at finding the determinant of the set of functions. If you're able to get 0 to be the determinant, then the condition has been what? Satisfied. You now conclude that the functions f1 and f2 are linearly dependent. So that is that. FMS 001419. You have raised your hands. So yes, what is the question?
Sir, one question is,
001419.
hello, sir.
Yes, I can hear you now.
Please, my question is with the first example.
Okay.
Looking at the book they gave to us,
Okay.
they solve the example and get to some point and add some constant k,
Okay.
which I don't understand. I don't understand where that constant is coming from.
It's coming from.
Yeah,
Okay.
because looking at it, if you are going to work without the constant, you are going to get zeros.
Okay.
But they introduce the constant there, and I'm making that and now show that it's linearly dependent. So I don't understand how that aspect is
Okay.
being worked.
Okay. So you realize that they are, as you go through the process of finding the unknowns, after expressing it as a linear combination, you realize that there are times that you get 0 for one of the unknowns, but the other two may not be 0. You see, if you get one to be 0 and the others to be non-zero, you have to conclude that it is not linearly what? Independent. So in that case, it is linearly dependent. The condition for linear independence of the set of vectors is that the unknowns, all the unknowns must be 0. And when the unknowns are 0, that is when the linear combination of the vectors that are given will also result to 0. So if any of them is non-zero, it means that the set of vectors are linearly dependent. Are you getting it?
So,
And
sir,
the K,
sir,
yes,
please, if you are going to if the first one is 0 and you are going to substitute it in the subsequent one, you are going to get all of them to be 0.
yes.
And now they
So,
introduce the constant.
yes, so yes,
And
I'm
now
getting your question. So in that case, it means that the solution for that expression, they are what? They are infinite. They are many. So in that case, you have to create an arbitrary solution for the what? The set of vectors. That is why they introduce K. Are you getting it?
Yes.
So
So,
the C,
sir, please.
yes.
Sir, so please, under which circumstance will you know that you have to add a constant to it before you now add the constant? Because looking at, we have another example where they did not add the constant, but they took it to be 0, 0, 0. And in this case, the first one, they add a constant. And they are the same, they are similar examples. I want to know under which circumstance will you add a constant, and under which circumstance will you will not add that you will not add the constant?
When you were solving in a matrix form, it was the solution in a matrix form.
Yes, sir.
Good. So you realize that when you get the last row to be all zeros,
Yes, sir.
that's what happened, isn't it?
Yes, sir.
Very good. So you realize that once you get all the last row, everything to be 0, it means that no matter whatever constant you get, when you multiply, it will give you 0.
Yes, sir.
Good. So that's why you can now introduce a constant. What we are saying is that your answers can be many. Or let's say your answers are many. Because if you choose a particular K, let's say K is 1, the solution will be the same.
Sir.
If you choose your K to be 2, you'll still get everything to be 0. If you choose K to be -3, you still get the right hand side to be 0. Is that not it?
Yes, sir.
Very good. So that is the reason for that introduction of the K. The K there represents scalars. So any scalar you choose, you still get the same thing, right? So
Yes.
anytime, so you wanted to find out under what condition. The condition is when you are doing your RREF or RE or whatever it is. Once you get the
Yes, sir.
last row, everything to be 0, you can introduce that K.
Yeah.
All right, so he's going to continue.
Thank you.
Welcome.
Thank you, sir.
I knew what you. So your question has been answered.
Sir,
Yes.
with the Ruskian method, I didn't actually get from the beginning.
You didn't actually get it.
Yeah, from the beginning, like I raised my hand up, but you were still solving. And with the latter part, you said when the determinant is equal to 0,
Okay.
you said it means F1 and F2 are linearly independent or dependent.
That is dependent, linearly dependent.
When the determinant is equal to 0.
Yes.
Okay. So I don't know if you can take from the beginning because I didn't actually get from the beginning.
Okay. So with the Ruskian method, when you express it, so the idea is that it is to guide us to find the determinant of the set of what functions that is given. I hope you are getting it.
Yeah.
Yes. So the Roskian is saying that if you find the determinant and then it resolves to 0, then you can conclude that the whole set of functions is linearly what? Dependent. I hope you are getting it. Okay, so let me explain. As I am saying, the Roskian is to guide you to find the determinant of the set of functions that is given. So when the determinant is equal to 0, Roskian is saying that you can conclude that those set of functions are linearly dependent. If such condition is not satisfied, that is, if it is not equal to 0, then the set of functions are linearly independent. Are you getting it now? FMS 010219. Are you getting it? Okay, so I think we can make the progress. Okay, there's another Godwin Kwesi. Godwin Kwesi, you can ask your question and then we will now proceed. Godwin Kwesi.
Sir,
Yes.
when are we closing that? Our data is running down.
Your data is running down. That's the question you're asking. And when are we closing? It's an hour meeting, so
Sir.
it's 2 hours.
Sir.
1 to 2. Okay.
Hello, sir.
Yes, I'm listening.
Yeah, I've got short of data and I joined the guy, so we are together.
Okay, so we can.
And I want to ask a question.
Okay, what's the question?
So looking at the independent distance, if a set of vectors are what independent,
okay,
like the unknowns, we should get them to be what? Zeros,
yes.
But if you are looking at the Roskian's method, no.
Okay.
If you are rather getting a 0 that is linearly what dependent, but not independent, so that means they are opposite to the. Okay.
Yes,
okay.
they are opposite with the one with the vectors.
Yeah, that's what I want to find out. Okay.
Okay, so that's I think.
Thank you, sir.
You are clear now. Okay, that's
so you want him to now tell you that they are opposite. It's a condition. So you just have to remember that when the Roskian is 0, the set of functions are linearly dependent. So that's something you put in your mind. If you want to use a Roskian to determine whether a set of functions are linearly independent or not, you can choose to use the Roskian. And once you use the Roskian, the condition is that when the Roskian is 0, then the Roskian is equal to 0, and it means that the set of functions are linearly dependent. So it's a condition. It has nothing to do with the other one. So get to that at the back of your mind. That's the condition.
Okay, there is also another method or way that when your question involves functions, if you choose not to apply the Roskian method, you can also look at trying to see if one of the function can be expressed as a scalar multiple of the other. So if such condition also is met, you can also conclude that the set of functions are also linearly dependent. If you're able to express one as a scalar multiple of the other, and then you can conclude that the set of functions are linearly dependent. So we will use this same example and then we apply that method. If you're able to express one as a multiple of the other, a scalar multiple of the other, then you can also conclude that it's linearly dependent. So either you use the Roskian or use this approach. So let's look at that. We are taking the same example. We are using the same function. And then we move to rank of set of vectors. So the function that was given was F1 because expo expo 2x, and then the second function is expo 2x to multiply x minus 1. And as I said, remember, we can expand this. Can be expo 2x minus 2. So this is the same as this. Yes, so we are looking at trying to make one a scalar multiple of the other. So we still go by the steps. So this is the proof to show how you can express one of the functions as a what? As a scalar multiple of the other. So as we were saying, if you express this as a linear combination, and it should be equal to 0. The condition is that so we have F1, maybe say a scalar of C1 multiplying the first function plus another scalar, say C2 of F2 should be equal to 0. So this is how we go by it, and this is how it is proven or it is shown. So you want to make one the subject, one of the function the subject, such that it is a multiple of the other. So you can now move this one. We are trying to make F1 the subject. So we may have C1 F1 equals negative C2 F2. And then finally, if you want the first function to be alone, then it's going to be F1 equals C2 over C1 F of 2. And these are scalars. C2, C1 are what? Are scalars. So you can now represent it by a common scalar, say K of F2. So if you're able to express one function to be a scalar multiple of the other function, when this condition is met, you can conclude that it is linearly dependent. So we are going to use this example and go through these processes. Find numbers for the scalars and then see if we can get this function or one of them to be multiple of the other. So let's look at that. So we follow the steps. It's the understanding that really matters. Get it, you can solve more examples. So F1 is given, the function 1 is given to be. So we don't know the scalar, so we can generate any variable to represent your scalar. So we can use the C1.
Break
Okay, so you can say that F2 should be equal to F1.
Okay. All right. I just want to make things simpler. So we have F2 is equal to U raised to the power 2x minus 2. Already you can see that this and this, there's some link. E raised to the power 2x, e raised to the power 2x. Now using your rules of indices, we can break this into pieces. For instance, if I have e raised to the power a minus b, is the same as e raised to the power a all over e raised to the power b. So e raised to the power a minus b is the same as e raised to the power a over e raised to the power b. Remember your indices. So once the bases are the same, you can subtract the exponent. So it's the same way I'm going to do that. So we have F2 is equals to, we'll break this into two. We have e raised to the power 2x all over e raised to the power 2. So I can further say f of 2 is equal to 1 over e raised to the power 2 times e raised to the power 2x. And the e raised to the power 2x is what we already know as f1. So you can say f of 2 is equal to what? 1 over e raised to the power 2 times f1. Now this 1 over e raised to the power 2, you can also make it e raised to the power negative 2. You can leave it like that. 1 over e raised to the power 2 is a constant. You know, e is it's called Euler constant. It's a value, 2 point something something. And even if you use your calculator, e raised to the power 2 will give you an answer. So this whole thing here that we see here, as he was saying, once you can express one of the functions as a scalar multiple of the other, then you conclude that the two functions are linearly dependent. So this one is a scalar multiple. So f of 2 e raised to the power minus 2 f1. So there is this e raised to the power minus 2. So this is a scalar. So once you are able to do this, then it means that the function f1 and the function f2. I think the previous example used the Ruskin.
Yes.
And it was 0.
Yes.
And you concluded that they are linearly dependent. And we are saying that if you can express, but of course, it is not all examples that you can use this. For instance, if you are given f of 1, maybe it's equal to sine something x, and then you have f of 2 is equal to cos. See that this one, there are two different functions, and so there's no way you can. So it is your ability to see the connection between the two functions and how you can express one as a scalar multiple of the other that can help you to be able to conclude that, oh, then these two functions are what? Are linearly dependent. Are you okay? Did anybody ask question? I hope there's no question. Okay. That's the charts.
Yes.
Look, who is that? You can't say after this example, let's end. Are you the lecturer? Huh? How can you say after this example, let's end? Okay, after this example, I'm taking over. Let me, where is it? On mute.
This person wants to ask a question.
Okay. Uh-huh.
Hello, sir.
Yes, go ahead.
So what you did now, I did not understand something.
You didn't understand the.
Yeah, what you just saw from the board right now.
Okay, but what did you hear?
So he said at the last aspect of it, he said you can use all the distance, the functions to
Yes,
solve
the one I actually did. What did you hear?
So the distance, the TA used was scale distance method to solve for the linear.
Yes, that's what he did. That one there is no problem. The second one he said, what did he say before I took over?
So that place I didn't understand. I didn't get him.
Oh, okay. All right. I'm sitting here, so I heard him. He said that one way of also showing whether two functions are linearly dependent or not is by trying to see if you can express one function as a scalar multiple of the other. you have got two functions, right? And you want to say, can you make one of the function stand and is equal to maybe k, then the other function? Are you getting it? So let's say you have an equation y is equal to 2x. Right? So you have y and you have x. And then the relationship between y and x is that y is equal to what? 2x. That's the same thing that we are going to, or you have two functions, f1 and f2. Then you can say f2 is equal to maybe 3 times f1. Meaning when you take 3 and you multiply by the f1, it will give you the what? The function f2. That's what we are doing here. And after talking plenty, I couldn't clean it. I told you that, can you see? I said that you can see that there's e raised to power 2x here, there's e raised to power 2x here. Can you see that?
Yes, sir.
Good. So it means that this f2 is related to f1 in a way. So, and this e raised to power 2x minus 2. Indices. You remember your indices? Have you done indices before?
Yes.
Yes. So
yes, I did indices.
Is the same as e raised to power 2x over e raised to power 2, or?
Yes.
Yes.
F of 2 is equal to e raised to power 2x over e raised to power 2. Can you say that?
Yeah, we can see.
Good. So if you can say this, then it means that f of 2 is equal to 1 over e raised to power 2 times e raised to power 2x. Can you say that?
So I can see that.
Good. Now this e raised to power 2x, what is it? It's not the f of 1. F of 1 is equal to what? E raised to. So it means in place of this e raised to power 2x, I can put f of 1 there. So f of 2 is equal to e raised to power minus 2 f1. I hope this one have no confusion. 1 over e raised to power 2 is the same as e raised to power negative 2. Do you agree? You agree?
Yes, sir.
1 over e raised to power 2 is the same as e raised to power negative 2. Huh?
Clear.
Good. Multiply by what?
Yes, sir.
F1. Multiply by F1. So it means that f of 2 is equal to this scalar, which is e raised to power negative 2, is a number. This e raised to power negative 2 is a number. If you use your calculator and you press e raised to power negative 2, it will give you a value.
Yes, sir. We understand.
Very good. So once you are able to do this, then you conclude that these two functions, f1 and f2, are linearly dependent. Or maybe I should let him go through what he wanted.
Thank you, sir. Sir, it's okay. Thank you.
What is simpler? In order to use this from what do you call this second method, you should have an eye to see the connection between the two functions. You should be able to see it. Once you see e raised to power 2x here, that should tell you that it means it's related to f1 in a way. So once we are using indices, this mathematics, e raised to power 2x minus 2 is the same as e raised to power 2x all over e raised to power 2. What is e raised to power 2? That's 1 over e raised to power 2 times e raised to power 2x. What is e raised to power 2x? That's f of 1. That is here. 1 over e raised to power 2 is the same as e raised to power negative 2. This thing here is a scalar. When we say scalar, I mean it's a number. You can use your calculator to find e raised to power negative 2. And so f of 2 is equal to a particular number times f1. And once you can express that, then this second method is saying that you can conclude that these two functions are linearly dependent. So this one is just an addition to what you've already done. Then I now went on to say that it is not all functions that when you are given, you can use the second method. And that's where I now said, give the example, f of 1 equals sine x and then cos x. There's no relationship. Can you relate sine x to cos x? It'll be difficult.
No.
Unless maybe you are dealing with the squares, maybe sine square something and those things. And you can find a way of using trig function to connect them. Apart from that, that will not
It's
tell.
even past time. Trop.
I hope you're okay now. That's it.
You know, just on the decision.